SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to this course on gas turbines and jet engines. So, today is the second lecture of this course. So, we are in week 1 of this course and today we will learn the basics of gas turbine components. Okay. In the previous class we have seen what is a gas turbine, what are its application, how it works at a very simple level. So, today we will get an overview of the different components involved, so that later when we study each of these different gas turbines and jet engines, we know already how the different parts are involved and how they work together. Okay. So, concept which will be covered today. So, we will cover the components, what are the major components of a gas turbine and what are the roles of these components, what does this component do. So, first we will start with the common components of gas turbines and jet engines, then we will see some additional components which are necessary for jet engines. What are the components of a gas turbine? If you remember the working principle, there were 3 major processes. One is that there is compression of fresh air. So, fresh air comes in from the atmosphere. Okay. So, this is the working fluid, passes through a compressor. So, compressor is one major device, major component. It compresses the air, which means that it increases the pressure. Okay. It increases the pressure. The pressure can increase up to say 10 times or 20 times also, depending on the design. Then this high pressure air goes into a chamber which is known as combustion chamber. In this combustion chamber, fuel is injected and the mixture of air and fuel is ignited, okay, and there the combustion or burning takes place, okay, burning of the fuel, which is the combustion process, and it generates, it is a very exothermic reaction, generates lot of heat. So, this combustion chamber is the second major part of the gas turbine. Then the third major part is the turbine. So, what happens is that after combustion we have combustion products, which is a mixture of unused air, means unused oxygen and nitrogen, and carbon dioxide and water vapor, which are the products of the combustion. So, this mixture comes to the turbine and it passes through the turbine, and turbine generates mechanical work. So, its role is to create rotation of the shaft and create lot of torque, so that it can run the compressor. So, part of the work which is generated by the turbine is used for running the compressor, rest of it is used for running other devices, like say if your requirement is to run a generator, the turbine will run the generator, or if your requirement is to run a propeller, turbine will run the propeller. Okay. So, turbine is there for generation of work and combustor is there for heat addition. So, these are the components again, the combustion the compressors are shown here, multiple stages, we have discussed this, combustion chamber and the turbine. Then this is for jet aircraft. So, there are additional devices like the nozzle, which we will discuss later. So, this is an actual image of a large industrial gas turbine, and you can see that how the different stages, what are known as stages of compressor and stages of turbine look like. So, these are all compressor stages, the yellow colored ones, and each of these is known as a blade, and in a single stage multiple, like several blades are mounted around the circumference of the hub or the base of this stage. Okay. So, this is known as a rotor disc. At the hub of the rotor, all these blades are mounted and the rotor itself sits on the shaft. Okay, the hub itself is connected to the shaft. So, when the shaft rotates, these blades also move, and they, while moving, because of their curved nature, they push air in the forward direction, which can be used up in following stationary structures which are not shown here. Stationary blades also are there, which are mounted on the casing. So, here we have removed the casing, so that is not seen. So, those then this high velocity air can be converted back to, means this kinetic energy can be converted to enthalpy. So, the work which is transmitted by the compressor gets converted to enthalpy. So, that is the role of the compressor. So, each stage does similar amount of work, and we need very large number of stages for large say turbines or large compressors, so that we can get very high pressure ratio. So, each compressor increases the pressure by, let us say, typical value will be 1.5 times. So, this will again increase 1.5 times more pressure, 1.5 times. So, if there are 10 stages, the pressure will increase by 1.5 to the power 10. Okay. Then there are the turbine stages. So, you can see this white color structure and grey color structures are the turbine stages. They are also similar in some respect to the compressor stages. There are multiple blades, several blades which are mounted on the hub, mounted on the shaft. Their working principle is the opposite of a compressor. So, here the air flows. So, if you blow air to a fan, the fan will start rotating because of the movement of the air. So, similar thing happens here. The hot combustion gases comes through nozzle and hits these blades, and as a result they push the blades start moving, and because they are mounted on the shaft, it also starts rotating the shaft, and the shaft is connected to the compressor. So, the shaft starts rotating the compressor. Shaft is also connected to external say devices like generators or propeller. So, they also run those external devices. Okay. So, this is how power is generated by the turbine, and at the exit of the turbine the energy of the gases have been, most of the energy has been extracted. So, the gases go out at low energy state, okay, and is exhausted to the ambient condition, to the atmosphere. Okay. So, exhaust gases go out to the atmosphere, similar to say car engines, automobile engines. Okay. So, let us see each of the component in more detail. So, main components, as I was saying, there are three main components: compressors, combustion chamber and turbine. Okay. Now, compressors again can be of two types. These are known as centrifugal compressor, which you see here, and then we will see later axial compressor. So, nowadays for modern aircraft engines, almost all aircrafts use axial compressor, but industrial gas turbines uses or can use combination of centrifugal and axial compressor. So, what is the nature of centrifugal compressor? Here the air comes in the axial direction, like in a gas turbine engine, air will come from the front, right. It comes from the front in the axial direction, but then it passes over a rotating structure. This rotating structure is known as a impeller, and it changes its direction to the radial direction, okay, towards the outside radius. It moves towards the outside radius, and in this case, because of the rotation, it creates a lot of centrifugal action on the moving air. So, the air gets accelerated, and then this accelerated high speed air can be passed through a diffuser to convert the energy to high pressure or high thermal energy. Enthalpy is increased. Okay. Then this is passed to the combustion chamber. So, this is the basic working principle of a centrifugal compressor, where the rotating impeller creates a lot of centrifugal action or centrifugal force which acts on the air, which compresses the air. Okay. Here you can see an actual image of a centrifugal compressor. There are two stages here. So, here you can see one stage, another stage here. Okay. So, when we have multiple stages, there are difficulties in designing and arranging these stages, because the centrifugal exit exits the air in the radial direction. The air has to be brought forward in a convoluted way back to the axial direction of the second compressor. Okay. So, which is more difficult to design this passage. But this type of compressors can generate lot of pressure difference in a single stage, up to 4 or 4.5, up to 5 also nowadays is possible, as compared to say less than 2 of a axial flow compressor. Initially military aircrafts or jet engines also have been made with centrifugal compressor. So, one of the two initial aircraft engines. So, if you know the trivia questions, you will know that the aircraft engine was, or the jet engine was parallelly developed in Germany by von Owen and by Frank Whittle in UK. Okay. So, UK design had centrifugal compressor, whereas the German design has the had the axial compressor. Nowadays all modern designs follow the German design of this using the axial compressor, but centrifugal compressor uses have remained in industrial turbines. Okay. Another example of a centrifugal compressor, you can see the centrifugal compressor along with the combustion chamber and jet pipe. Okay. So, that is for a jet engine. So, now coming to the other type of compressor, which is axial flow compressor. So, the axial flow compressor on the other hand works by taking air in the axial direction similar to centrifugal compressor, but also exiting the air. Okay, the air also goes out in the axial direction. So, this is exactly similar to the fans, normal fans, say which you see on your ceiling. So, ceiling fans, okay, or table fans, where the fans rotate by using a motor and it pushes the air forward. Air comes in axially, so like comes towards the fan blades and moves out axially. Same thing happens in the axial compressor. Only differences are that the number of blades are more and they are more curved and more elongated, means more have larger width, so that more compression can be done in a single stage. So, these are similar to some of the exhaust fans that are used in domestic application in houses. Okay. So, generates lot of compression, but not as much as that of centrifugal compressor. So, the main advantage here, there are multiple advantages of this axial compressor. One is that of course, the flow direction is very much suitable for a single linear structure like a gas turbine. So, all the flow occurs in the direction of the shaft. So, flow comes in and goes out in the same direction, will go to the combustion chamber and to the turbine also in the same direction. Okay. And second is that the cross sectional area is less if you compare for the same inlet area, because the same mass flow rate if we are designing, then the cross sectional area is almost equal to the inlet area, slightly larger, whereas for centrifugal compressor the cross sectional footprint, cross sectional area is much larger than the inlet area. So, for jet engines this poses particularly, means for jet engines this poses lot of difficulty, because of this very large cross sectional area of the centrifugal compressor, there is lot of drag, whereas if we use axial compressor the engine cross sectional area is small and drag is significantly less. So, that is why for jet engines we use axial compressor. Here you can see on the left hand side another image of a jet engine compressor with very large number of stages. So, you can see the low pressure stages which have larger blades. Low pressure stages are the stages where the pressure of the air is lower and gradually the pressure increases when it passes through the different stages. So, the density increases, specific volume decreases. So, for the same mass flow rate the passage area needs to decrease. So, the length of the blade gets decreased. Okay. And in many cases there are multiple shafts. So, the smaller blades can rotate at a faster speed because they undergo less centrifugal, they have less centrifugal stress. So, they can rotate at a faster speed, whereas the large blades of the low pressure compressor needs to rotate at a smaller speed. Example from an actual engine of a actual turbofan engine, the core section you can see the multiple stages of the compressor, axial compressor, and these are how the different stages are arranged. So, you will have one stationary guide vane which guides the flow to the first stage rotor. So, these are mounted to the casing, then the first stage of rotor mounted to the shaft. The shaft is rotated by the turbine which rotates the compressor blades. So, unlike a motor which is used for say fans, in this case the compressor is directly driven by the turbine. Okay. It is a direct connection is there, direct drive is there to the turbine, no gears or no other mechanisms are used. So, almost entire power can be transmitted to the compressor. So, again there are fixed blades for guiding the flow and increasing the converting the kinetic energy into enthalpy, and this process goes on until the flow goes out axially. The size of the blades keep on reducing. Then we have the combustion chamber. Combustion chamber is the device or the system where the combustion takes place. So, here you can see this can be of again different shapes, this can be of tubular structure or annular structure, We will study this also in detail later on towards the midway towards the course, okay, or around the midpoint of the course. But now let us just have a quick look at this combustion system. So, what is done is air comes in at a from the compressor with a certain pressure and gets divided into multiple groups. So, part of the air enters from the initial part which is known as primary air, then rest of the air is gradually introduced and fuel is injected in this location near the primary air. So, the main combustion starts place in this region by using a igniter, and then more and more air is used to bring the combined temperature to a suitable temperature, so that the turbine blades do not fail. The energy still remains, but the mass is increased, so that the temperature goes down. So, the role of this combustion chamber is to assist with this combustion process, have continuous combustion with less emission and have very uniform temperature variation at the introduction to the at the inlet of the turbine. So, very uniform delivery of the combustion products, and the combustion should be fully completed within the short time which the combustion products or the gases have in this combustion chamber. So, this time is of the order of means much less than a second. So, we need the combustion to be completed before that. Okay. So, we will go into further details later on. These are some examples of the mechanisms what happens in combustion. As I was saying, the air is introduced to different steps, and these are known as primary air, cooling air, dilution air. There are internal channel means structures which are known as liner, which protects the outer casing from the hot combustion products, and then there is the outer casing which acts as a structural component, because this combustion chamber is like a pressure vessel, because we have air at very high pressure, right, after the compression. This is how it looks like in 3D. Okay. Then finally, we have the turbine stages. The turbine stages we have already seen in the in one of the initial slides, look similar to the compressor stages, but works in the opposite fashion. So, the turbines stages are pushed by the combustion products, and as a result they move and rotate the shaft. Okay. And they also have similar blades, but the blades are more curved for turbine stages, and each turbine stage can generate more means it can undergo more pressure ratio, it generates more work as compared to the work input to a single compressor stage. So, less number of turbine stages are required even for industrial gas turbines, and for jet engines even less number of turbine stages are required. Okay. This is how this shows a closer view of turbine stages. So, this is one stage, and you can see each of these blades which are curved, and then within the blade you have cooling channels, and the blades have a particular aerofoil shape. So, that the flow comes in and goes out smoothly from this and generates a change in direction and momentum, and resultantly there is a force on the blades in this direction, okay, which causes the blades to move in this direction and creates the rotation. There are also structures which are there at the end of the blades to keep the blades secure. These are known as shrouds, and these are also important, because otherwise there is tendency of the blades to deflect and also to get elongated due to creep. So, these are the major components for a gas turbine. These are also the major components for a jet engine, but there are some additional components required for jet engines. So, before finishing the class, we will quickly discuss those. So, three main additional components are required. One is known as the diffuser. Okay. So, unlike gas turbines, industrial gas turbines, jet engines are designed to operate at high speed. So, a typical jet engine may operate, passenger aircraft jet engine may operate or move forward at a speed of Mach 0.9, just below the speed of sound. So, which will translate to around say 300 meter per second. So, this high speed air related to the engine, the air is coming towards the engine at this high speed. Okay. So, we can use this extra energy which is present in the air to do partial compression. Okay. So, we can reduce the workload of the compressor, we can reduce the number of compressor stages by converting this high speed air or the kinetic energy to generate a large pressure ratio depending on how much is the speed. So, for example, for very high speed aircraft it can be even larger, and there are experimental aircrafts where the compressor is not needed at all, okay, like ramjets or scramjets. Anyway, for normal aircraft there is a section which is known as the diffuser. You can see this front section before this fan blade. Here this is acts opposite to a nozzle. Okay. Here the cross sectional area gradually changes such that the flow velocity decreases. Okay. Flow velocity decreases, and as a result the pressure increases. So, you will need less pressure in the compressor. Okay. So, these are used for almost all aircraft engines, because these are some of the most important say ways to reduce the number of compressor stages, and as a result the number means complexity and the weight of the engine. So, this is from a GNX turbofan diffuser, large aircraft engine, and this is another diffuser. This is another type of turbofan engine, but which has mixed type exhaust. Okay. Rolls-Royce Trent 700 diffuser. You can see the long diffuser section here. Then the second important part is the jet engine afterburner. These are used for military application. So, what is done is that after the gas turbine, after the turbine stages, after all the other components, there is a long duct which is known as afterburner. So, here additional fuel is injected here in this region, and because lot of air still remains in unused condition, lot of oxygen still remains, okay, in the combustion products. Why they remain in the combustion products? Because gas turbines have combustion at very lean conditions, means very large amount of excess air is used to keep the temperature low. So, here that extra air is used along with extra fuel which is injected for secondary combustion. This process is known as afterburning, and the advantage of this is that because there are no moving parts, no rotating parts after this, we can take the temperature to very high temperature here, which was not possible in the combustion chamber due to the presence of turbine. Here there is no turbine after this, so we can take the temperature to say 2000 Kelvin also with suitable say lining material for the bypass, means for the afterburner and for the nozzle section. So, this high energy fluid then can generate very high velocity exhaust gases which can increase the thrust, but this comes at the cost of efficiency. So, the efficiency gets decreased, but these are used for situations where efficiency is not important, but the high thrust is the main requirement. Okay. So, for example, military aircrafts in combat situations, in trying to evade missiles, in taking off from short runways, you can see the afterburner is running here when this F-18 Hornet is launching from an aircraft carrier from a very short runway of the aircraft carrier, and the afterburner operation is clearly visible because of the very high temperature in the afterburner. The exhaust gases are glowing, unlike the exhaust gases that you see from a commercial jet engine which does not use afterburner. Similarly, here the exhaust gases are glowing and they are coming out at very high speed. So, you can see the shock waves also when this aircraft is flying with afterburner operating. So, they are used only intermittently whenever maximum thrust is required, but they have very high fuel requirements. So, they cannot be continuously used. Okay. And the third component, which is the most important, most important component for jet engine out of this, is the jet engine nozzle, because without this we cannot generate thrust. So, the nozzle is like a typical nozzle as you understand it say from common sense. So, it increases the velocity. The function of the nozzle is to increase the velocity of the combustion products. So, the combustion products come at high pressure and means relatively high pressure after the turbine and high temperature. So, there is lot of energy in the combustion products, and this combustion products can be taken to low pressure. So, can be accelerated in the nozzle and the exhaust gases will come out at high speed. Okay. So, this has a converging area. So, typical nozzles that we know of has converging area, these are known as convergent nozzle. For very high speed applications, there can be convergent divergent nozzles also. You might have seen them for rocket engines like say space shuttles or other rocket engines. You will see that the nozzle is actually the area is increasing. So, that is the diverging part of the nozzle, which is a very counterintuitive thing which we will study later, that for supersonic condition increasing the area increases the speed of the fluid, while in normal condition, subsonic condition, we understand that decreasing the area will increase the speed. Okay. So, you can see how the nozzle acts, again the same diagram showing that the nozzle is accelerating the fluid, the nozzle cross section area is decreasing nicely and it is accelerating the fluid, okay, creating the thrust. Here you can see the inner nozzle of a two nozzle, like these are known as turbofan. So, two nozzle which has one inner nozzle, hot nozzle, and one outer nozzle which is not shown here directly, cold nozzle. So, this is from the Pratt and Whitney turbofan, high bypass turbofan engine. Okay. This is another example of jet engine nozzle. You can see that this is a convergent nozzle, the size is gradually decreasing, which is the typical case for most aircrafts, unless it is like a very high cost, high speed experimental type aircraft like scramjets. Otherwise, we can use convergent nozzles, and these have other features, like these have movable flaps. These flaps overlap more or less depending on how much cross sectional area is needed, which controls the, which is needed, like it needs to change based on the volume flow rate through the nozzle. This is from a military aircraft, okay, and you can see how the nozzle shape varies. So, we will finish this class with this small discussion on the different components. I hope that you have got a nice overview of the different components. You now have an understanding of what are the different say parts which are present in a jet engine and in a industrial gas turbine. Now, from the next class onward, we will start with the technical details of each of these gas turbines, and later we will go through the jet engines. Okay. So, we have learned in this class the major components of a gas turbine, which are the compressor, combustion chamber and turbine, how they work at a very basic level we have learned, so that we can study the overall systems as we will do in the subsequent classes. When we study them, we have the basic knowledge of the individual components also, we are not in blind. Okay. And the second is, we also learned additional jet engine components like the diffuser, nozzle and afterburner. So, these are the references, and with this we stop today's class. Thank you, and we will meet again in the next class.